So today I will tell you a little bit about Gap-ETH and its implication. So let's start with what Gap-ETH is. Before lunch, as we saw in Saket's talk, we have seen the exponential time hypothesis, or ETH. To state it briefly, it says that if you have a tree set with n variables, then you cannot solve it exactly in 2 to the little of n time. So you cannot decide whether it's satisfiable or not. Now, why should we believe in ETH? Over the years, there are a lot of lower bounds on how to solve tree set. In particular, these are lower bounds for specific class of algorithms. One example is sum of squares algorithm. So it's known that if you want to use sum of square type algorithm, then you need essentially exponential time. But it turns out that this running time lower bound also holds for approximate version of tree set as well. So for that, given that it kind of makes sense to also make this hypothesis, which is now called Gap-ETH. So the hypothesis says the following. There exists some constant delta, let's say it's 0.001, such that you cannot, in sub-exponential time, distinguish between a tree set formula that is fully satisfiable versus the one that is not even 99% satisfiable. Okay, or like 1 minus delta fraction satisfiable. So of course, as you have seen from the first talk by Subhash already, given the PCP theorem from ETH, you know immediately that this gap version of tree set also cannot be solved in 2 to the n to some small constant time. But in recent years, there are better and better PCP theorem. And currently, if you assume ETH, then you almost get Gap-ETH, except that you lose some polylogarithmic factor in the exponent. So you get a lower bound that is 2 to the n over polylog n instead of 2 to the n that we want in Gap-ETH. We'll come back to this question a little bit later in the talk. But the other direction is obvious, right? If Gap-ETH is true, then ETH is true. Now, of course, there is another hypothesis, which is a strong ETH, which was also mentioned in the previous talk. We will not use this in this talk, but it implies ETH. But as far as we are aware of, there is no result between the relation of Gap-ETH and SETH. So assuming SETH, we don't know whether Gap-ETH is true. Okay. Now, for most of the remainder of the talk, we will see how you can use Gap-ETH to prove hardness of approximation. And for most of my talk, I will focus on parameterized problem. And as you already saw in the previous talk, I'll discuss first 2 problems, K-clique and K-dominating set, and then we'll go on to other problem. So of course, K-clique, we are given graph, an integer K. We want to determine whether there is a clique of size K. K-dominating set, we have a graph and an integer K, and we want to determine whether there is a dominating set of size K, which just means that each vertex has to be in the dominating set or is a neighbor of one of the vertex in the dominating set. And here, K are the parameter in both cases. And we want to know whether there is an FPT algorithm for this problem, meaning that the algorithm should run Fk times poly n time. Okay? These are stuff from the previous talk. And from the previous talk, we also know that these problems are hard. In particular, they are complete for the class W1 and W2, respectively. But for this talk, we will focus on the approximation aspect of these problems. And in particular, we are looking for FPT approximation algorithm. So we are looking for an algorithm that runs in FPT time, so Fk times poly n, and has approximation ratio Gk, where G is some function of the parameter K. Okay, so this for clique, this just means that you are promised that there is a clique of size K, and you are okay with finding a clique of size K over Gk. For dominating set, it means you are okay with outputting a dominating set of size K times Gk. So since the very early day of parameterized complexity, there have been questions about what can you do in terms of parameterized approximation. Can you do 1.01 or 1.1 FPT approximation for these problems. And in fact, we don't know how to do this. In fact, we don't know how to do anything at all. In particular, for k-clique, the only thing we know is to output, say, one vertex or a constant number of vertex. That's order of k approximation. And we didn't know whether we can get little o of k approximation at all. So even k over log n, let's say, or k over log n was not known. Similarly, for dominating set, in the dominating set case, it's not even known whether you can get any function of k at all. So even 2 to the k approximation or tower of k approximation was not known. And yeah, the short summary is that under Gap-ETH, we can show that both of these are not possible. So there are no non-trivial approximation algorithm for k-clique and k-dominating set under this particular setting. Okay, and just to remind you of the complexity assumption, again, there are two types of complexity assumption. Today, in this talk, we're mostly talking about ETH and Gap-ETH. But there are also parameterized assumptions, which we saw in the previous talk, W1 versus FPT and W2 versus FPT. The ones I state here are the engineer's version, as Saket said. And there is also another kind of nice assumption in the parameterized setting, which is a kind of a gap version of W1 not equals to FPT. I will not use this directly in this talk, but it's kind of nice to know. Basically, it says that if you have two CSP in the parameterized setting, where you parameterize on the number of variables, then it's hard to approximate. Okay, so this is the PIH assumption. And there are some obvious relation that you can see between them. Again, it's not too important for now. But an interesting thing here is that, as you can see, the assumption above here, we don't have any gap in the assumptions. Okay? Whereas the assumption below, we assume directly that some problem is hard to approximate. So if you start from assumption below this red line, it will be easier to prove hardness of approximation because you already have a gap. So the only things you have to do is to either amplify the gap or do reductions that preserve the gap in some way. Okay? Whereas if you have to work with the assumption above the line, you have to create the gap yourself. You start from exact problem, you have to create the gap. And this is where the PCP theorems and so on comes in. But for the purpose of today, for this talk, we will not be talking about assumption above the line that much. And in particular, we will be just focusing on Gap-ETH. Okay, and just before we go forward, I just want to quickly mention that very recently, just last year, there is a breakthrough from Guraswamy and others that shows that PIH holds under ETH. So this is truly a gap-creating reductions, kind of a somewhat of a PCP in the parameterized regime, almost. But I will not talk too much about that because you will hear about it from Bing Kai tomorrow, so I'll leave it to him. Okay, so this is the kind of assumptions that we will be talking about. And so about 10 years ago, when I started looking to this problem, there are not too many papers on this topic. Basically, there are only a few papers. I'm definitely missing a few here, but roughly speaking, there are only 3-4 papers on this topic. But over the past 10 years or so, there have been so many papers on this topic using these various assumptions to prove the different hardness of approximation for parameterized problems. And again, these assumptions, some are weaker than the other. In particular, Gap-ETH is a pretty strong assumption. So for many of these problems, we knew the hardness of approximation from Gap-ETH first, but now we also know hardness of approximation from ETH as well, for the weaker assumption as well, since we have now more tools. So given this, I'll try to focus on just a few problems that can give you some flavor of what you can do from Gap-ETH that we still do not know how to do from ETH. Okay? And these problems are, you already saw dominating set clique, but I will also talk about bi-clique and densest case subgraph as well. And we will come back to the definition later. It's not too important now. Okay. So let's start with k-clique. So what do we know about k-clique? So from the previous talk, we know the exact version is W1 complete. We also know that if you assume ETH, you cannot do too much better than just the enumeration algorithm, where you enumerate over all the k size subset, right? That takes n to the k time, and you know you cannot do fk times n to the little o of k time. That's for the exact version. How about the approximate version? So Bonnet et al. Shows that if you assume Gap-ETH, then you cannot get any constant approximation for k-clique. So this is kind of interesting because this is a paper kind of before Gap-ETH, but they basically proved this before Gap-ETH was formulated. And later we show that in fact, not only you cannot get any constant factor approximation, but you cannot get any non-trivial approximation at all. Okay? In particular, for any g that is little o of k, if you want gk approximation, you need n to the k over g time. Okay? And n to the k over g is the trivial time because you can just enumerate over all subsets of size k over g if you want g approximation. Okay? And in particular, for any little o of k approximation, you cannot get it in FPT time. And actually, what we prove is something that we call inherently enumerative. So what inherently enumerative says is the following. Suppose that we now have a gap problem where I promise you that either a clique size is at least r or less than k. Okay? And here r is arbitrary, r and k are arbitrarily large constants such that r is greater than k. Okay? So r could be arbitrarily large, could be 2 to the k or Tower function of k. And I ask you to distinguish between these two cases. Now, obviously, you can do the n to the k approximation again as before. But what we show is that you cannot do anything at all. So you cannot do n to the little o of k. So there is some delta such that it requires n to the delta k time to solve this problem. Okay? And we will see this proof now. This proof is actually quite simple, but it will lead nicely to the hardness proof for biclique and others that we don't know from ETH. Okay, so we want to show this. I just copied it from the previous slide. So what should the reduction look like? We start from Gap-ETH, right? So what does Gap-ETH say? It says that if there is an instant, a three-set instant, then checking whether it's distinguishing whether it's satisfiable versus whether it has value less than 99% takes exponential time. So this is just the starting point of our assumption. And here I let little o of n to be the size of the set instant and the big N to be the size of the clique instant that we will construct. Okay, so what we will construct is a clique instant such that the size n, big N, is roughly exponential in little n over k, such that in the yes case, you have that the clique size is at least r, and in no case is less than k, right? Since the size, the big N, is 2 to the little n over k, and the O lower bound is 2 to the n, you have that the new running time lower bound is big N to the k, right? Okay, good. So we will just look at how this reduction works. Okay, I just copy the reduction that we want from the previous slide. And this reduction is, in fact, the FGLSS reduction that Subhash also mentioned in the first talk, but stated slightly differently and in slightly different parameter regime compared to the NP world. Okay, so again, assume we have some three-set formula, right? And I use M to denote the number of clauses. And we can assume without loss of generality that M is linear in N. This is due to standard sparsification technique. Now, how are we going to create our clique instance? So here is how we will do it. We will take random subsets, R of them, where each subset is a subset of order of M over K clauses. Okay? So each subset has 1,000 m over k clauses. Okay, so each subset contains 1,000 over k fraction of clauses. And then for each set Si, we will create one vertex for a partial assignment to Si that satisfy all the clauses in Si. Okay? And then we just join two vertices if they are consistent, meaning that they don't assign the same variable differently. Okay? Just to give you an example here, let's say our first set is just the first clause, our second set is the second clause, right? Then in this case, there are 7 satisfying assignments for this clause. So we'll create 7 vertices here. So for 0, 0, 0, this is a satisfying assignment. 0, 0, 1 is not a satisfying assignment, so we don't create that vertex. And then we create one for 0, 1, 0, and so on and so forth. We do the same for the other clauses. And then we add an edge if the two of them are not contradicting. They don't assign the same variable differently. So the first two has an edge. This also has an edge. But the top left and the bottom right, they assign x3 differently. So they will not have an edge. Okay? So the edge check that they are consistent. Okay, and that's it. That's the entire reduction. Right? It's extremely, extremely simple. Kind of as like it's kind of the first reduction you would try actually, and it works, sort of. Yeah. And this is what I mean by it's much easier if you start from strong assumption like Gap-ETH. It's very, very easy to create gap, to amplify gap if you have some already, compared to if you start from an exact problem where you have no gap whatsoever. Okay, so let's take a look at the analysis quickly just to make sure that we are on the same page. So what is the size of the instance? We have R sets, right? And in each set, there are at most 7 to the number of clauses satisfying assignment. So the number of the total number of vertices is at most R times 7 to the 1,000 m over k. So this is exponential in order of n over k as we claim. So this is good. How about the yes case? So if there is a satisfying assignment, then what do? We just pick one vertex per each of Si that is corresponding to that satisfying assignment. Okay? So those, since it comes from the same global assignment, it will form a clique. So you have a clique of size k. Okay, that's very simple. So the only thing left for us is to prove the soundness, which is the no case, which is to prove that if we start from the instance with value less than 99%, then the clique size will be less than k. And for this, you can think of it multiple ways, and we'll see another way of thinking about it later on. But one easiest way to think about it is to talk about disperser. So we say that a collection of subsets S1 to SR is this k epsilon disperser. If when you look at any k of them and take a union, it covers almost everything. So it covers at least 1 minus epsilon fraction of all the elements, and here the elements are the clauses. Okay, so if you think about the bipartite graph, you can think of bipartite graph where the left-hand side are the set, the right-hand side are the elements, and this is saying that if you pick k on the left, then the neighbors, it covers at least 1 minus epsilon fraction on the right. Okay, and it's a pretty weak object in pseudo-randomness, and it is weaker than things like extractor. And it's pretty easy to construct. If you take a random subset, you will get that it's an k epsilon disperser with high probability. If you take it so that each set size has at least a constant over k fraction of elements, it will be k epsilon disperser with high probability, and you can de-randomize it. It's not too complicated. At least for the parameter regime that we want, it's pretty easy to de-randomize. Okay, now to go back to what we want to prove. In the soundness case, recall again, we want to prove that if the value of the starting instance is at most 99%, then the largest clique size is at most k, right? Is less than k, right? So let's assume contrapositively that it's at least k. So what do you get? So you have a clique of size at least k in your graph. So let the vertices be from set Si1 to Sik. Okay, now since there are edges between every pair of them, it means that everything is consistent. So this corresponds to an assignment that satisfies all the clauses from SI1 union SI2, so on to SIK. Okay? But what did we just say? If we pick S1 to SR at random, then they are dispersed with high probability. In particular, K of them, if we take K of them and take a union, it will cover more than 99% of the clause. Okay? And this means that all these clauses that are covered in the union, it has to be satisfied by this assignment. So this means that the value of the set instance is at least 99%. Okay? So this is the entire proof. It's very simple. And it's basically the same as the original proof, except with a slightly different parameter regime. Yes? Right. We sort of do graph product implicitly and do a subsampling. So actually you are getting a little bit ahead. So I will present that version of the interpretation in a moment. Is there any more questions about this? Yeah.
How big R can be again?
Yes. So here I'm thinking of R as a constant, but you can take R to be as large as n to some small constant. Yeah, so n to the 0.001, depending on the delta in the Gap-ETH, it would still work. Yeah. Okay, if there is no more question, let me give another interpretation of this reduction that is kind of a graph product, like as Amir said, which will be useful for us in a ladder reduction. Okay. So the interpretation that I would say will be the following. So in this reduction that we just saw, we do a direct reduction, right, from 3 set instance to a click instance, and the size is as we intended. But in a new interpretation, let's think of it as the following. We will first create a graph G prime that is a lot larger than the graph we want at the end. Okay? And then we will do a subsampling from the graph G prime to the final graph G. Okay? And here I'm calling the size of the graph G prime n prime and the subsampling probability P. So here I'm thinking of P as just n over n prime. Like if you want to be super formal, you have to be a little bit more careful, about independence and the expected size versus the real size. But for the purpose of this talk, I will completely ignore those just for simplicity. Okay, now as you can see, I kind of leave the yes and the no of this G prime in the middle. So let's think about this together. So if we want it so that after we subsample with probability P, we get clique of size at least R in the yes case. What do we want in the middle here? Okay, so we are subsampling, just to be clear, we take G prime and we subsample each vertex independently with probability P.
Should have size, click size R or P.
Yes, exactly. So you need click size to be R over P. Okay, so that if you subsample each vertex with probability P, then you get a clique of size roughly R. Okay, again, this is roughly, but I will just take that to simplify the discussion here. How about the no case? What should we have in the no case? Pardon?
K over P.
K over P. Well, okay. You can ask whether it's enough to get a clique of small size in the middle instance, but it turns out that it's not quite enough. So you can create a graph with a lot of small cliques, so that after you subsample, at least one of them will survive. So what we actually want at the end is we want to count the number of K cliques in this middle instance and say that it's small. How small? If you want like a trivial bound, is 1 over P to the K. Since we are keeping each vertex with probability P, each K clique will survive with probability P to the K. Right? So if the number of K cliques in this middle instance is much less than 1 over p to the k, then the number of clicks that will survive in the end in expectation is less than 1. Okay? So this is what we want here for the middle instance. Okay? So now let's reinterpret what we just did in terms of this kind of creating a large graph and subsampling framework. Okay, so let's take a look at our O construction. It turns out that this intermediate graph can be constructed almost the same way as what we did, with one exception. So previously, we take random subsets of the clauses. Here, instead of taking just a random subset, we just take all the subsets. Okay? So we take all the subsets of size 1,000 m over k clauses. Okay? And that's it. That's the construction of the intermediate graph. Okay? Just to recap what we did is for all subsets of size 100 m over k, which I now denote by t, we'll create one vertex for a partial assignment that satisfies that subset. Okay? And the edge are checking the consistency is exactly the same as before. Okay? And you can sort of view this as a kind of a product version of the graph, except that we are taking subsets instead of a direct product, which could contain the same element. But that construction would also work. Okay, so this is our intermediate graph. So let's check and make sure that it satisfies the property that we want. So first, what's the size? The size is now at most m choose t, right? Because there are m choose t subset. And for each subset, again, there are at most 7 to the t satisfying assignments. Okay? And just to make things easy, we can think of p directly as subsampling to what we want. Okay? So we will subsample with probability r over m choose t. So after subsampling, it will be r times 7 to the t, the size of the graph at most. Okay? Which give us the size that we want. Okay? Now how about the click size? Okay? The click size is also kind of obvious by the setting of p here, because r over p is exactly m choose t, which is the number of subsets. And if we have a global assignment, then we can just project that global assignment into each subset, and that form a big clique for us of size m over t. Okay, so those two ways done. So the only thing left for us to prove is that the number of k cliques are small. So, and in particular, we will show a bound that is something like m choose t to the k times some term that is exponentially small in n. Okay, and note here that m choose t to the k is kind of the bound that you would have gotten roughly in the yes case, because you have a clique of size m choose t. So if you count the number of k clique, it's roughly m choose t to the k. But in the no case, it will be much smaller, and that's the point. And how much smaller? By exponential factor in the n. Okay? And I'll not check the parameter here, but you can kind of easily see that it goes through. Okay, so how do you bound the number of k cliques in this intermediate graph? So this is what we want to show. If the value of the tree set instance is small, then the number of k clique is small. So let's take a look at any k clique. Okay? Again, similar to before, this k clique, since the edges check for consistency, it corresponds to some partial assignment to the instance. Just to be very formal, let's define that partial assignment to be what I call flattening. So for this case, you can think of flattening as just a union of all the vertices. If you think of each vertex as this assignment of xi being 0 or xi being 1, you can think of flattening as just a union. Okay, so for example, in this case, x1 is assigned 0, so in the flattening, it also has x1 equals 0. But x2 is not there in any vertex, so x2 is not there, and x3 is 1, and x4 is 0, and so on and so forth. Okay, so how do we count the number of k cliques? Okay, so we can count it by first count all the number of possible flattening, and then count the number of cliques per flattening, right? How many flattening are there? Each flattening is a partial assignment. So each variable has only 3 choices. Either is in there and being assigned 0, in there being assigned 1, or it's not there at all. So at most 3 to the n. How about the number of click per flattening? How many of them are there? If you fix the flattening, let's think about how many vertex you can choose for that flattening. If you fix the flattening, then what you can choose is you can only choose a subset Si that contains just the satisfying assignment for that particular flattening, right? But that flattening can satisfy at most 0.99 fraction of the clauses, since that's our assumption. So the number of choice for each vertex in your clique is at most 0.99 m choose t. Okay? And this is the gain that you have. Instead of m choose t, you get 0.99 m choose t. Okay? That's the number of choice per vertex, and since you can choose k of them, it's at most 0.99 m choose t to the k. Okay? And you can see that since we set t to be n over k, this is you gain an exponential factor, or you lose an exponential in n factor due to this 0.99, and that's why you get this 2 to the minus omega n at the end. Okay, and this is also kind of an important point. Like you need t times k to be at least n, right? So that the factor that you gain here dominate the 3 to the n over there, right? Otherwise, this argument wouldn't work. Okay, so this is kind of the reinterpretation of this clique in terms of this graph product and then subsampling. Okay, or like randomized graph product, as some people call it. Okay, so I hope everyone is still with me. So next, we will go to something that we actually do not know how to prove or to nearly prove at all under ETH. Okay, and that's the k by clique problem, or k balanced bipartite graph problem. So in this problem, we are given a bipartite graph, okay, and an integer k. The goal is to find a complete balanced bipartite graph that is as large as possible, which I just call k by clique here. Sometimes people call it like k balanced by clique, but I will drop the balance here. So for example, here k equals 2. This would be the balance by clique that we want. Okay. Now, what is known for this problem under in parameterized complexity? Interestingly, even though it looks very simple, this problem was not known to be hard in parameterized complexity for a long, long time. It was called one of the most infamous open problem in FPT by Downey and Fellow in their book. And it wasn't until 2015 that Bing Kai resolved this question, and he showed that k by clique is W1 hard. Okay? But in terms of running time lower bound, the running time lower bound is still not tight. So he got n to the square root k for by clique under ETH. Now, what we can show under Gap-ETH is quite interesting. So firstly, if you assume Gap-ETH, you still get a result kind of similar to before, that you cannot get little o of k approximation in FPT time. Okay? So in some sense, it seems in FPT time, you cannot get anything non-trivial because the k is the trivial thing again. Outputting just a single edge give you k approximation. But in terms of running time lower bound, what we get is it depends on the approximation ratio you want. But if you want to rule out constant approximation, we also only get n to the root k running time lower bound. Okay? And one of the things that is interesting here is that even after all the development of the last 3-4 years, for example, clique is now known to be hard to approximate under ETH, but for by clique it still remains open. Okay? So under ETH, we still don't know whether k by clique is hard to approximate, even to factor 1.001 in FPT time. Okay, just even forget about the running time lower bound aspect. Just asking whether it's in FPT time you can get 1.001. That's still open under just ETH alone. Okay, but under Gap-ETH you can prove something fairly strong like this. Okay, and it turns out that we kind of prove almost an inherently enumerative thing like the clique. So remember in clique, we say that the hardness between the two cases is if there is a gap, between k versus r, where here is k is the smaller parameter and r is the larger parameter, then you need n to the k time. So that's for k click. What we can show here is you need n to the root k time, okay, for by click. Okay? And indeed, I'll now go over this proof. And this proof indeed goes through the framework that we just discussed for click. Okay? In particular, what we will do is that we will try to reduce from a 3-set instance, similar to before, to a by-click instance where there is a gap. But now the size of the instance is not exponential in n over k. It's exponential in n over square root k. Okay? And that's why we get a lower bound that is big N to the square root of k, instead of big N to the k, as in the click case. And we will follow the framework as before, as in we will construct an intermediate graph that is big and then do a subsampling. Okay? So everything is the same as before so far. And again, the soundness and completeness will also be of the same format as well. So in the yes case, we will show that the by-click in the intermediate instance is at least r over p. In the no case, we will show that the number of by-clicks in the intermediate instance is at most 1 over p to the 2k. Okay? And now there is a factor of 2k here just because now you are selecting 2k vertices. Right? So a k by-click has 2k vertices, whereas a k click has k vertices. That's why there is a factor of 2k here. Okay? And then after subsampling, you can see with a similar argument as before that it satisfies all that we want. Okay? So what we have to show is just how to construct this intermediate graph. Okay, so turns out the reduction is almost the same as well, except with one small twist. Okay, previously we were taking subset of clauses. Okay? The only change here is you take subset of variables instead of the clauses. Okay, so instead of taking t clauses, now you take all subsets of t variables. You look at the partial assignment on them, and you create one vertex for each such partial assignment on each side of the graph. Right now the graph is a bipartite graph. Okay, and for the two vertex check, you also have to check a little bit more. So when you want to join two vertex, before you just check that they are consistent, but now you check that when you join them together, you don't violate any clause. Right? Meaning that if a clause is completely assigned, if the three variables are completely assigned by the union, then you shouldn't violate it. Okay? So just to give you an example, right? Now 1, 2, 3 is not a clause, but now we are looking at all the partial assignment on t variables, and here t is equal to 3. So we will create all the eight vertices for x1, x2, x3, and so on and so forth. Okay? And we do the same on the right as well. And for the first two, we add an edge since they are the same. For this one and the second one on the right, we don't add an edge because they are not consistent. Right? This is the same as before. But moreover, if we have a vertex on the right that is like x1 equals 0, x2 equals 0, x5 equals 1, then we will not add an edge from left to right as well, because this violates the first clause, the x1 or x3 or x5, or not x5, sorry. Okay, so this is how the graph is constructed. Okay, is the graph construction clear? Okay. So what is the size? The size is, now we are taking subset of variables instead of clauses, so the size is n choose t times 2 to the t. Okay, and again, we can set the subsampling parameter to be r over n choose t. So this we set because we know that if we have a global assignment, then that global assignment induces a clique of size n choose t, right? Because for every subset of variable, we can just restrict that global assignment to that subset, and we will have that huge clique of size n choose t. So if we set p to be this r over n choose t, then we will satisfy the constraint that we want in the yes case. Okay? So we are only left with the no case. So we have to show that if the instance has small value, then the number of k by clicks are small, in particularly much smaller than 1 over p to the 2k. And in particular, we will show a bound that is kind of similar to before. So you have a term n choose t to the 2k, which is the term that you would have had in the yes case, but you have a gain of roughly 2 to the n here. Okay, you have a drop of roughly 2 to the n. So far everything is very similar to the k-clique case. Okay, but this no case proof will be a little bit harder, and I will not go into all details, but hopefully I can give you some intuition here. Okay, so I'm just copying what we want for the no case from the previous slide. If the value is small, want to show that the number of bi-clique in this intermediate graph is small. Okay, now let's consider any bi-clique. Let's try to do the same thing, right, and see how it goes or how it breaks down. So let's consider any bi-clique. Okay, any k bi-clique here, and let's look at its flattening. Now recall that the flattening is the union of everything, right, of all the assignment. Now there is a little bit of a difference here because our graph is bipartite, so we should look at flattening of both sides separately. So here I'm looking at a flattening of the left-hand side and the right-hand side separately. Okay, and now we will do the same counting. So the number of k bi-clique, how can we bound it? We say how many flattening are there, and for each flattening, how many k bi-cliques are there. Again, the number of possible flattening is exponential in n, and we will show that the number of k bi-clique per flattening is something like n choose k to the 2k. Again, that's the term that you would have had in the yes case, except there is a drop. But the drop now, it looks a little bit mysterious, but it's 2 to the minus kt square over n. Okay, whereas previously it's just k times t. Okay, and if you look at this term kt square over n, you want this term to dominate that n term, right, for this bound to work. And that's why you need this t to be n over square root k here. Okay, and this is why we get a running time lower bound that is n to the square root k instead of n to the k in the previous case. Okay, and once you have this, then you get the bound that you want. Okay, now instead of doing the counting of bi-clique, I will show something a little bit weaker, but it will give you the same flavor of the argument. So what I will show is actually I will just show that the size of the largest bi-clique, okay, is at most n choose t times 2 to the minus t square over n. Okay. Note that this is weaker than that because if the bi-clique is larger than that, the biggest bi-clique is larger than that, you can take any k of them, and if you count those k bi-clique, then it will be more than this, right? So this is a weaker goal that we have to prove. Okay, but just to check again, so in the yes case, we show that there is a bi-clique of size n choose t. So here we get this drop of 2 to the t square over n. Okay, so we will prove this slightly less ambitious goal here. Okay, so to prove this, let's take a look at the flattening, right? So we have to examine this a little bit more carefully. As you can see, it looks something a little bit weird. The two sides are not the same, and sometimes the variable also appears in kind of a funny way. So it turns out that if you think about it, there are only a few ways that the variable can appear. The first way is that it appears on both sides and it appears with the same value, right? So this I will call a good variable because they are kind of consistent on both sides. But there is another kind of bizarre situation where one variable can appear on one side, being assigned both 0 and 1, and does not appear on the other side. Okay? This can happen because we don't require any edge on the same side. So they don't have to be consistent. Okay, so they can appear twice on the same side with different assignment. I call this a bad variable. And finally, there are some assignment that maybe doesn't appear at all or appear just once on one side. So these I call the ugly assignments. Okay, so we have the good, the bad, and the ugly. And now again, instead of considering all possible flattening, I will just show you a proof in the case where, in the extreme case, where all the variables are either good, or all the variables are bad, or all the variables are ugly. Okay, just to simplify the proof a little bit, but it's pretty easy to generalize. And before we go there are a couple of observations to make here. So the first observation is that every vertex on the left is just a subset of size t of the flattening. Right? This is just by definition, because flattening is a union of everything. And the second observation is that if you look at the flattening on the left and on the right, the total size is at most 2 times n. This is because every vertex can appear at most 2 times in total on 2 sides. Right? Either they appear once on both sides, or they appear twice on one side and they cannot appear on the other side. Okay, so these are the 2 observations we'll use. Now let's look at these 3 extreme cases, starting from the easiest case where every variable is ugly. And again, ugly means that that variable appears at most once in total on both sides. So if it appears at most once in total and on both sides, then the second observation can be improved by a lot, right? Because each variable appears at most one in 2 sides. So the total number of appearance in the flattening is at most n, right? So now what does this mean? This means that at least one of these sets has size at most n over 2. So if you then use the first observation, you know that each vertex is a subset of size t of a set of size at most n over 2. So you know that the number of vertices on that size at most n over 2 choose t. Okay, this is using observation 1. Yes?
Wait, why is there not a case where the variable appears twice on one side and once on the other side?
Yes, so if it appears twice on one side and once on the other side, then you see a contradiction, right? If you have like x1 equals 0, 1, and then 0 here, then there will be no edge between x1 equals 1 and x1 equals 0. Yeah. So basically, we are still checking the consistency on the different side, but within the same side, since there is no edge requirement, we cannot check their consistency. Yeah. Okay, so in this case, we get this bound, and if you just check this out, then this term is already smaller than the claim bound. So this is good. This is the easiest case here. So the next case to consider is the bad case. And this is a harder case, but I think it encapsulates this argument pretty well. So what is bad, right? Bad is if each variable appears twice on one side. Okay? Every variable is bad. Every variable appears just twice on one side. Then what happens? So let's say both sides are balanced, just for simplicity. So half of the variable appears twice on the left, and the other half of the variable appears twice on the right. Okay? Then if I look at, the intuition is this. The intuition is, if I look at the t size subset of the left flattening, right? The left flattening now has size n, right? So the number of t size subset is n choose t. But if you look at them, most of the time, this t size subset will have x1 equals 0, xi equals 0, and xi equals 1 together. And that's not a valid vertex, right? Because when we construct a vertex, each vertex assigns each variable only one value. Okay? And indeed, this is a kind of a birthday paradox situation going on here. In particular, if you think about each xi as like one birthday, and if you think about drawing t of them randomly, right? Then the number of collision in terms of the birthday will be roughly t squared over n. This setting is slightly different because there is some dependency, but roughly speaking, it's the same in the sense that you can show pretty easily that the expected number of I, such that both xi being assigned 0 and 1, appearing in the same vertex is roughly t squared over n. And this, you can turn it into a probabilistic bound, showing that the probability that this doesn't happen at all is exponentially small in t squared over n. Okay? And only those vertices are the vertex that are valid. So that means that among all the n choose t subsets, only that much fraction, 2 to the minus t square over n fraction is valid. And that's why we get this bound, that the bi-clique size is at most 2 to the t square over 2 to the minus t square over n times the n choose t. Okay. Obviously, I'm skipping a lot of details here, but hopefully it gives you some flavor of how this proof goes. The last case is actually very similar to the previous case, so I will just go over it quickly. If every assignment is good, what does it mean? This is actually going back to more or less the clique case, because it means that the left and the right are exactly the same. The flattening are exactly the same. Okay? But if they are exactly the same, then it means that it has to violate 1% of the clauses. So let's look at any violated clause, x1 or xj or xk. My claim is that if this is a violate clause, then any pair of variable cannot appear together. Let's say xi and xj cannot appear together in a vertex. Why is that? If xi and xj appear together on the left, then you can look at the vertex that xk appear on the right. Right? And there can be no edge here because the union of these two violate this clause, right? So our graph wouldn't have put, our construction wouldn't have put an edge here. Okay? So what does this mean? This means that for every violated clause, this xi-xj pair is a prohibited pair that cannot appear together in the same vertex. Okay? And again, you can use a similar argument as before, that if you pick t random t elements subset, then you see roughly t square over n such pair. And with the same argument as in the previous case, it means that most of the subset cannot be a vertex here, cannot be a vertex in the bi-clique here, and you get the same bound as before. Okay? I know that's a little bit compressed, but I hope that at least that gives some intuition for this proof. Okay, so that's the hardness for bi-clique. Okay, but as I promised you, there is one more problem that I want to talk about, which is densest subgraph. Okay, so in densest k subgraph problem, you're given a graph and an integer k. You want to select a subset that has as many induced edges within them as possible. Okay, now of course this problem is as hard as clique because k-clique. If you can solve densest k subgraph, you can solve k-clique. So the exact version, the hardness follow from k-clique. But how about the approximate version? Well, it turns out, again, under, say, ETH, it's still open how to prove hardness of, say, factor 1.01 for densest k subgraph for FPT algorithms. But if we assume Gap-ETH, we can actually use the hardness from our bi-clique result that we just saw, and I'll tell you how to use it in a moment, to show a pretty strong hardness for densest k subgraph. So on the one hand, if you want very large factor, you can show that in FPT time you cannot get k to the little o 1 approximation for any function little o 1 in the exponent. Okay, so you cannot get like k to the 1 over log k, for example. And if you want a strongest running time lower bound, this one is a little bit weak. So you can show you cannot get constant approximation, but the running time lower bound is n to the root log k. Okay? And the trivial algorithm here is only n to the k time. And as far as I'm aware of, there is no better than n to the k time algorithm known for constant approximation. Okay? So let me just quickly tell you how you can get this result very easily from the bi-clique that we already showed. So what we use is this classic theorem of covariate, Schwarz, and Turan. So what the KST theorem says is that if you have a bi-clique free subgraph, graph that doesn't contain any bi-clique, H bi-clique or H bi-clique free graph, then it's pretty sparse. How sparse? So the densest graph has like k square edges. Here you have k square minus 1 over h edges if it's H bi-clique free. And roughly speaking, it means that like a random graph is almost the densest possible, or just almost. Just a quick note, this is a very big distinction between bi-clique and clique, right? So in clique-free subgraph, you can be very dense, right? Like a Turan type graph would be very dense. Okay, and now you can get the result fairly easily. So just to recall that for k by clique, what we show is that, and here I'm swapping the variable here, that if you want to distinguish between by clique case greater than k or less than h, you need n to the root h time. So then we can create the same, just use the same instant for DKS, okay, for instance, k subgraph. In the yes case, since there is a k by clique, there is a k subgraph that has a k square edges, or order of k square edges. But in the no case, you just apply the KST theorem, right? That tells you that any k subgraph, since it's h by clique free, it can have at most h to the 2 minus 1 over h edges. So this gives you a gap of k to the 1 over h. Okay? Now this immediately gives you the k to the little o 1 hardness because we know from the hardness of k by clique that the left problem is hard for any h that is omega of 1. Right? So if we plug that in to gap of k to the 1 over h, then that gets a gap of k to the little o of 1. Okay? But note here that if you go through this kind of argument, you will never get a polynomial hardness or approximation for densest k subgraph, because you would if you want a polynomial in k hardness, you would need h to be a constant. But if h is a constant, then that's easy, right? If your graph is h by clique free for constant h, you can check that in n to the h time. Okay, so that's kind of the limitation here. And similarly, if you want just a constant hardness, then you can set h to be just log k. So if you set h to be log k, then you get a running time lower bound that is n to the root log k. Okay, and again, this is also another limitation. Like even if you prove the tight running time lower bound for k by clique, if you go through this argument, the base running time lower bound you get for densest k subgraph will be n to the log k, right? Because you need h to be log k. You cannot let h to be larger and get a constant gap. Okay, so those are most of the technical results that I want to say. Just a couple of quick notes before I go to the, yeah. For Gap-ETH, yes. For Gap-ETH, yes.
And these are the highest lower bounds in general,
there
right?
are some lower bound that, I'll mention them, but it's under a little bit more like strange hypothesis, you could say. So as alluded to again by Amir, you can actually prove better lower bound, but under some more exotic assumption. Just to give you an example, one possible assumption is an ETH for random tree set. Okay, so what does it mean? It means that in 2 to the little o of n time, you cannot refill a random instant of tree set. So you cannot distinguish between a random tree set instant and one that is fully satisfiable. And if you do this, right, then you can actually get a better running time lower bound for k by clique. So you get n to the omega k. So that's like the right running time lower bound. Okay, and another assumption I will mention is this. Let me not go into too much detail, but it's about a planted clique hypothesis. So basically, if you assume that in the planted clique problem, you can solve it pretty easily in n to the log n time. If you assume that you cannot do that in n to the little o log n time, you can actually prove very strong hardness result, including for densest k subgraph. So for densest k subgraph, you can prove that basically k is the best. You cannot get anything little o of k, similar to what we got for clique at the very beginning of this talk. So it's totally inapproximable. And running time lower bound is kind of the same. So if you want O1 approximation, you also have to spend n to the k time. You cannot do anything better. And again, this kind of result also give like other implications as well. But these are assumptions that are a little bit more exotic, and these results are not known under Gap-ETH. Okay, so maybe I will summarize this talk with some open questions. So in terms of open question in FPT, like I think we can classify the problem into two set of problems. One is the problem that we know under Gap-ETH, and we want to prove under weaker assumptions. And another is problem for which even under Gap-ETH, which is already very strong, we still don't know how to prove. Okay, so let's go to the first one. So these are results that are known under Gap-ETH, but not known under ETH. For K-clique, total in approximability, the one that we saw at the beginning of this talk, whose proof is like extremely simple, is still not known under ETH, but it's almost known. Okay, so now the running time, the approximation ratio that is known is already k to the 1 minus little o of 1, but there is still some little o of 1 factor in there. Okay, so that's still open. For bi-clique, this I think is perhaps the most interesting one. As we already saw in the second reduction, we cannot get even little o of k approximation, right? In FPT time, if we assume Gap-ETH. So that's extremely strong. You cannot get any non-trivial approximation. But under ETH, I don't even know how to prove 1.01 hardness, right? So this is an interesting question. And of course, you could ask for even stronger hardness, but even constant factor hardness, we don't know. And this is a graph, basically the same status as K by clique. Okay. How about Gap-ETH? So what is still out there that we don't know how to prove even under Gap-ETH? So for K-clique, today we talk about this FPT approximation regime where we think of the completeness as also being FPT. Like exactly your question when you ask about how large can you take the R. So here we think about R as some function of K. But you could take R all the way to polynomial in N and ask what happened. And in this case, if you just do the reduction as is, you get the completeness as N to the 0.01, where the 0.01 comes from the constants in the Gap-ETH. You could ask, can you push it all the way, right? As Subhash mentioned in the NP hardness regime, you can get the N to the 0.9999 versus N to the 0.001. But that has to go through this basically parallel repetition. But if you do parallel repetition, you lose the exponential running time. So is there some way you can prove it without having to go through parallel repetition? It's not super clear. The same thing with dominating set. Again, dominating set, we now know that you cannot get any function of k approximation, but it's still open whether you can get lower bound that is log n, like maybe divided by some function of k. So the base bound right now is roughly log n to the 1 over k. By clique, again, n to the omega k running time lower bound. As I said, currently we only know n to the root k under ETH or Gap-ETH. And this is true even for the exact version. Okay? Even for exact version, we still don't know n to the k running time lower bound, even if you assume Gap-ETH. Right? Whereas, as I said, if you assume this more exotic assumption, you can actually get n to the k running time lower bound. Then this case of graph is the same, basically the same question. And also the total in approximability, whether you can get little of k hardness of approximation. Finally, another interesting problem is 2CSP. So for 2CSP with k variables, again, you can get k approximation trivially. I had a paper with Irit that shows that you cannot get k to the 1 minus little o 1. And recently, there is also a paper that got that from ETH. But in both cases, there is still a little o 1 factor there. So it's not completely little o of k. So that I think is still a pretty interesting open question. Okay, there are also implications of Gap-ETH beyond parameterized complexity, but I will skip those. But of course, I want to end with kind of the elephant in the room here, right? Which is whether you can prove Gap-ETH from ETH. Right? I think that's the most interesting open question there. And of course, this is related to linear size PCP. Like if you can give a linear size PCP with constant soundness and constant query complexity, then of course you get the Gap-ETH from ETH directly. But currently, what we only know is a quasi-linear size PCP. There are some development recently, but it's still quasi-linear size, even though the soundness is now better. Like one thing I want to highlight here is that this PCP try to work more or less in the polynomial time regime, right? All this PCP are trying to do the reduction in polynomial time. But note that since we are assuming Gap-ETH, we do have more running time to do the reduction, right? This is similar to sparsification, for example, where we know that we need exponential time to do the sparsification. So I don't know, like maybe there is some technique out there that can exploit the running time a little bit more to try to help us answer this like ETH versus Gap-ETH kind of question. Yeah, okay, and with that, I think I think that's all I want to say. Thank you very much.
Any quick questions? Let me ask a quick question. So is there any insight as to when you would use clauses and variables? Like you started with partitioning clauses.
Yeah, so for by-click, I didn't say it, but the intuition is that if you go through the k-click reduction and it actually fails, like there are some cases where the clauses are kind of partitioned into multiple partitions. They are not expanding enough that the reduction fails, and that's why we go through the variable instead. Yeah.
Is that person again?